Everyone, it's April 14th, 14th, 16th. Jesus. Alright, so, man, yesterday this problem was pretty hard, and I just tried it again. Like, I did a little bit tweak, but it got me a wrong answer. So, this method definitely is not right. So, I'm not going to even keep considering this. I have to think about a new solution. There's a hint, so we probably can look at the hint, but maybe take a look at the topics first, and then go for it. I guess the topic is greedy, like dynamic programming and greedy. Like I know. Oh, actually, I was dynamic programming, but I didn't really use greedy. I don't know how to do greedy on this. It like screams greedy to me, but I don't know how. All right, anyway, we're gonna do the challenge first. All right, this is the old problem. Convert it to a greater tree given the root of a binary search tree. So right now we have the topic is binary search tree. I think this is the third problem in the past 3 days we're doing binary search tree. I'm going to convert it to a greater tree such that every key of the original BST is changed to the original key plus the sum of all the keys greater than the original key. Okay? Less than is on the left, greater than on the right. And I think everything is unique. Do I return? I return a new tree. So everything larger than, right? So we want every key of the original BST is changed to the original key plus the sum of all the keys greater than the original key. So for 4, everything larger than is 5, 6, 7, 8, which is what? 26. Okay. I see. So, I remember this problem. So everything larger than, so for the root, everything larger than this is on this side. So I just need a subtree sum of this. Then we're done, all right? How about the ones here? So I need, so the right subtree, yes. And then what? And then I need everything here because I am the left subtree of my root. So I need to know the root value. What is the root? Maybe we should go right subtree first because on the right side, like 8, it's just 8, the rightmost, right? And then 7. And then we only need the rightmost. Well, the rightmost, and you don't know if you are a right subtree to a root, then all you need is your rightmost, and that's it. So along the right side. So if you are the left subtree, you need a right and you need a root. So that is the thing. So what do we need to do? What we need to do is, so we go right. And then if the rightmost is going to return 0. So we're just going to be plus 0, right? And then after right, let's say we return to the root. Okay? So right to the root. And for the root, I simply plus this thing, right? Because this is everything to the right, plus itself, right? So plus it, and then we go to the left, right? Now we go left, and we pass my value to the left. And for this thing, go right. And then once in here, we pick this and pick this up. So that is, and then when we return, back to this, but it doesn't change because something here is smaller, it doesn't change. So we'll now return back here. So this one will add this, past 21, and then, okay, this seems viable. Oopsie doozy. What did I do? Alright, so this is not working, yeah. This is yesterday's. I forgot to commit it. copy for today. All right. No test case. All right, so I think what I do is I will return the original tree, all right? But what I do is I give it a root. Oh, hold on, I need to pass something. So no, I'm def helper. All right, we have a node, which is I can say optional tree node, right? And parent pval, okay? Pval is gonna be int, and then return a tree node. Okay. So what do we do? We say if not node return. Oh, do we return? We actually return a. What do we return? We return an int. So return 0, right? Otherwise, we have, then we first do, say helper node.write. If we go node.write, then pval is 0. Okay? So once blah, 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 blah. Actually, do you even need to do the return? I don't think we need a return. I don't need a return. Okay? So this one will handle my write subtree. So everything is done. Now, once it's done, we're going to say node.val plus equal to node.write.val, my write subtree. Okay? Actually, we need also plus pval. Okay? Also plus pval. So plus equal to this. So that's me, right? When I'm done. After I'm done, I'm gonna do my left subtree. And into my left subtree, I'll pass my value. My value is everybody larger than me plus me. And then we got the left subtree, so I am bigger than all of them. Okay, then we say helper node.left and node.val. Okay, so once we're done, what do we do? Once we're done, if not node, return node.val plus if node, then helper node.write. Node.write, so it doesn't do anything. And node.val equals node.write.val. We don't have a write. I don't like that. Let's do it this way. If not node return, okay, and maybe it's easier to use the return value. So I can just say, so the return value is return the current node value, right? if it's the current null value, then we can return this plus this. And then its return value, I don't really care. Then we just say helper root and 0 and return root. Let's see. See if it's right. None type. I forgot to return something. If, let's say, I'm always returning, I need to return my, like after I handled it, I need to return node.val. I need to return my value. It's not correct. So we got 8. 3 didn't get 33. Huh. Right, it's not right. Think again. Traverse, alright? So we have a node, so node.val will equal plus equal to helper, so we go here. And then we go here, and then we go here, and then if node, so node.val equals plus equal to the right is 0, and then the p is all 0. So if I'm back, so this is 0, right? And then we go node.left. Node.left, no return 0, but I'm not receiving anything, so I return. Okay, so here's a scheme. I return node.val. Okay. So now I return to 7. Do I have 15? I do have 15. So 7 plus this becomes 15. And then I go to the left, and that's nothing. So we're back to, well, actually I have 21 as well. Yeah, we do have 21. Okay, we have 21. And then that's 6. And then we don't have, we have 26. And the 6 will come to the left, pass 21 to it, so 5 will be 26. Oh, 5 will be 26. We shall return this thing, because I don't have 30. We shall return this thing. This is just the left, right? So when I return the leftmost, so the leftmost is the entire tree, the sum of the entire tree, and I return to this, okay? Then I say I pass it on to the left, we pass 30 to it, right? And then if we pass 30 to this, and this one on the right. Yep, let's try this. Return this. And right. You're saying after I'm done, I shall return what? Like if I have some more, they're all larger than, so I should return this value. So this one shall propagate back to, so I shall return the the leftmost node, right? The leftmost, including myself, the leftmost. If I don't have leftmost, I return myself. If I have leftmost, I return the leftmost. So I go to the rightmost. I go to the rightmost node, right? And then I want to know the total, because so these are larger than me, right? Even including these are larger than me. So I want to know the leftmost node in this whole system. Yeah, the leftmost system will have, let's say if I have something left, which is smaller, right? And then everything here is larger than this. So it'll be this plus this is the total one. So I need to return this value back to 6. Not this one, this value. Oh, does it matter this value or this value? Technically speaking, it's the entire sum of these things for the right subtree. Right? So for me, I have a right subtree, so I need to compute the entire sum of my right and to here. And if I'm a left subtree, right, then I need to compute the entire thing of this and then this. So what do we do? For me, the first step shall compute the entire thing towards my, we'll go to the right tree. The purpose is to compute the entire thing here. Right, once we compute the entire thing, I return this value, return the sum of everything. Okay? Return the sum of everything. And then to here, and I want the sum of everything. Okay, sum of everything here. That to make me, but I need to return the sum of the entire thing. So I need the sum of this as well. But I don't need a sum on the left. I do need a sum on the left. All I can do is, for this, I do the right, and I would just keep going to the left. Right? Because I go right, if I keep going to the left, that will be the smallest. That will be the smallest value is larger than this. So its value is this value. Okay? So what do? We go right, and then go right until we cannot go right anymore. I'm going to turn here, and we go left. And we need to go all the way down the left. think it is just to compute the subtree sum. Okay, how do we compute the subtree sum? If not node, return 0. Okay, otherwise I can say else sum, let's say helper, node dot left, eval, right sum equals, oh, we should go right sum first. Right sum equals helper, node dot right, eval. So this one will compute the right subtree, and once we compute the right subtree, I update my value. Okay, update my value is going to be right sum plus p-val. So that is my update value. And then I want to find the left sum, which is node.val. After done that, I need to return. So I have the left sum, I have the right sum. So we need to return the total, right? So right sum plus left sum plus, oh, be careful. Be careful. So the sum, hold up, the sum is the total sum. So I think node.val is already a right sum plus right, oh, and also has p-val. Oh, hold up. So when I save it, so temp equals node.val. And then we change. Node.val is already changed. So we have to go temp plus the right sum is the total sum. The left sum is also the total sum. So we do that. Okay, let's try this one. All right, this one's right. Yeah, just to compute the left sum, compute the right sum, we just need to do a little bit trick in between. So now the idea is, can we avoid this node.temp? Yes, we can. All we need to do is, instead of temp, because node.val, so we can just say node.val plus this minus p-val, because I added p-val. And then we don't need this one. Yeah. Try this. All right. Got it. So I think this is optimal, right? This is optimal. Pretty optimal. Again, check my previous answers. Oh, it's about the same time that I solved it. Ha. So this is 5, 3, 8. All right, so how should we describe it? So this is a modified, right? A modified problem to find the sum of the entire tree. For each node, right? For each node, its value, right? Its value must add to the sum of the right subtree, and it must also, right, add its parent's value if it is the left branch of its parent. So based on this, we can use the algorithm to find sum of a tree, but add a parent val when passing to the subtree. When calling, right? When calling the right subtree, the parent val is set to 0 because yeah, this is nothing that's larger than. So it has to be 0. And initially, it has to be 0 initially. Is set to when calling the right subtree from the root. Yeah. Otherwise, the parent val is either the current node's val if passing to the left subtree, or some parent val inherited from previous iterations, from previous recursions. I hope it makes sense. It's ON. So what do we say? So this is so node's val must include the right subtree sum and its parent val if exists. Right, we have this. And then left sum. So when going to the left subtree, we supply the updated node's val because it has recorded the sum of all nodes that are larger than any node, than all the nodes in the left subtree. We return just the sum of the subtree. Okay, that's good. Take a look at the solution and the previous attempts. Yeah. Yes. That's exactly the same as what I had this time. Second solution. Sum of the nodes visited. Oh, holy guacamole. Oh yeah. We do right root left. Right root left is in the reverse order. I didn't thought about it. I would do right. This accumulates a total, and then this plus a total, and then yeah, so the right, and then we add the root value, and root value equals this. Very nice, very nice. This is a good. Wow, official solution is pretty good. Let's write it, just for fun. So this is the official solution. It does it. So going right, root, left is naturally the reverse order of all values. So we just
use the two tabars are next to the same.
Yeah, but I washed them.
Where are
One is here. The other is here.
I don't use the ones up there.
I saw it and I just grabbed it. Alright, back. So I say it's right, root left is the reverse order of all that. So we just keep track, right? Keep track of the total. And we have the value to add to each node. So I can just say self.total equals to 0. Right, and then we'll say def helper node. We don't have to return anything. And we just say, okay, what do we say? If not node, if node, I don't have to if not node. We say if node, right, then we'll do helper node .write. And then self.total always at node.val. Yeah, node.val equals self.total. And then helper node.left. Blah 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 blah. Once we're done, we call helper node and return root. Try this. I know it's slightly different from this, but it's fine. See the benefit of always running it first. Root. Yeah, it can kind of make you wonder. And I define the self here. I can do the self on the outside. But that's fine. Okay, so we're done with this. Back to the struggle. Yeah, let's take a look.
You have time, can you sharpen a knife tomorrow?
Oh yeah.
It's kind of hard to cut.
Oh yeah, sure. Dynamic programming and math. Didn't say anything about greedy. It looks very pretty. Okay, so it is dynamic programming, but how? So my scheme. So this, let's just delete this. This is not right. This ain't right. This is completely wrong. So I think if it is like we start from 1000, the worst we can do is O(n) squared, right? So what? We start from 1 to reach that. Start from 2 to reach that. Start from 3, right? All the way into the same. And how do we... Let's find 7, okay? So 6 we say, I think yesterday we found 6. 6 is what? 6 we can have 6 or 6 is 5. Okay, so we can go 1, 2, 3, and then go 3, 2, 3. That's 1 step plus 3 step plus 1, so 5. Yeah, 6 should be 1, 5. But that's a possibility of 3. Okay, 1, 2, 4. And then I have 2. So that's why we say 2 or 3. 7. Because the 7 is interesting. 7 is, that's a 10. Oh, that's the old solution. Yeah, we have 7 wrong. 7, it says is 7. Really? So we 1 plus 6. That's already 6. Oh, I can't. I see. 6 should... Wait, hold on. No. Oh, if I go 1 to 6, I'm already ending. That's the end. We end at 2. And 2 to 1, we cannot go. Ah, that is true. So 1 to 6, we cannot go. 2 to 5. No, wait. Why? Why 1 to 6 we cannot go? We can do 1 to 1. Right? And then hold on. We copy 1. That's one step. And then it's already there. We copy it. And then we say we have 1. We want to go to 6. And that's 5 steps. Alright, this is weird. This is something I don't understand. How come 7 is 7? Just so we already have 1, right? Yeah, we have 1. And now we say copy and then paste. One to 2, I say 2 steps. So you just paste. And 1 to go to 3. So paste, paste, paste. So we have 3 paste. So it's 3 steps to 3. And then we need to copy again, that's 3. And we need to paste again. Oh, I cannot copy 3. I cannot paste, 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 because I already have 1. So we just copy, paste, paste, become 3. Oh. Figure out new DP scheme. How do you get this stuff anyway? We have a copy, right? Definitely. And then the next step, it has to be paste, right? So we're gonna copy and paste. Now we have end up 2. now we have a choice, right? We can either copy or we can paste. Okay, so we bifurcate. So if we copy, then we still with 2, but our copy becomes 2. If I paste, then we have 3, and copy is 1, right? And then for each, again, it's a choice. So I can say, I want to copy. No. So if you copy, you gotta paste, right? So you copy, and then paste. It becomes 4. And this one, we just paste. Okay, so it's copy and paste. This is paste. All right, so on 4, again, we can choose copy and paste. That'll become 8. If I just paste, remember, copy is 2, right? Now if I just paste, that'll give us 6. Okay? So in here, it's paste is 3. So each one, again, I can choose copy and paste, which give me 6. Or I can choose paste again, that give me 4. Right? And then 4 is already reached, so this one is now good. So 4 is this path. 3 is this path, right? And 8, 6, both good. So 6 can be reached from 2 different ways. And then we can attach. So it's a 6 and 2. This is 6 and 3, right? So now I want to find 7, so I focus on the small, so 6, right? Oh, we need this one as well. 4 will be 1. 8 will be 4. Hold on, let's try this. Let's draw this one out. Okay, so we start from 1, right? And then we have to do copy and paste, get to 2 with current as 1. Terrible drawing. Hold on. 1. We do copy and paste. We reach 2 and 1. And then we can bifurcate. We can either copy and paste, get a 4 and 2, or paste just by itself and get to 3 and 1. And then 4, we can copy and paste, get to 8 and 4, or we can choose paste, which gets 6 and 2. 3, 1, we can copy and paste, get 6 and 3, or we can paste, get 4 and 1. 8, copy and paste, we get 16 and 8. Paste, we get to 12 and 4. 6, 2, we can copy and paste, get to 12 and 6. Or we paste, we get to 8 and 2. 6, 3, copy and paste, we get a 12. Oh, we'll get a 12 with 3. Or we paste, get to 9 and 3. No, 6 and 6. I have the same value. Yeah, the same value. So now 3. So 4, 1, we can copy and paste, get to 8 and 4. Or we can paste, which get to 5 and 1. Right? So we have this tree just start growing. Right? Starts growing. How big this thing can grow? Yeah, this can grow tremendously. The left branch is always a double. Okay. The right branch is the sum. The right branch is the sum. The left branch is a double. Hmm. So look at the 12, right? 12 have many different ways to get there. I can copy paste, and just paste. How about 9? 9 is I paste, then I double, then I paste. 1, 2, 3, 4, 5, 6. 6 steps. 10 and 2. Say reach 5. We don't have it. So what are we saying? We're saying we do reach value 1 and end up as 1. Okay. You know, if value 2 end up at 1, I have value 2 end up at 1. It's 2 steps. 2 steps, right? So value 1 end up, that's actually 1 step, right? And so for 2, I want to check. So 2, I can do 1 plus 1 or 1 times 2. So for 1 plus 1, I need to find a 1, 1, and then do a 1 more paste. So that'll give me 2. If it's 1 plus 2, so we need to find 1, 1, and we can copy and paste. Well, actually, no, we need to find, yeah, we find 1, copy it, and paste. We just copy, and then we paste. All right? Just copy this value, and then paste. And then we will end up at 2, 1 as well. So anyway, so that's the start. So we won't end up at 2, 2. So that's what we have. So now 3. So okay, we say we want 3, 1. Right? We're going to find 3, 1. Which means at the end is 3 and 1. Right? The value is 3, and then with current is 1. Actually, hold on. So again, with 3, we can check 1 plus 2. Right? 1 plus 2, what does that mean? Right? What does that mean? Or I can say 2 plus 1. So we need to find the previous is 2, 1, and then we can do a paste. And we have a 2, 1. Right? So we have 3, and then we end up 1. So 3, 1, we have a 3. And then 3, I cannot do double. Right? I cannot do double. So, okay, so there's only 3. 4. Okay? So 4, I can do 2 times 2. Or I can do 1 plus 3 and 2 plus 2. Actually, 3 plus 1 and 2 plus 2. And 3 plus 1, so we need a 3 and 1, and then we do a paste. So 3 and 1 is 3 steps, so it's 4 step, and a 4 step with a 1, right? So 4 step with a 1. Okay, so that's that. And 2 plus 2, so we need a 2, 2 situation, but 2, 2, nothing, so this one cannot be done. Okay? Now we can also do a 2 plus 2 situation, right? So this requires me to find 2, and then with anything, it doesn't really matter what. And then we find the smallest among these, and then the smallest among these, and then we just double. So copy and paste. So we need plus 2. So the 2, what we have is 2 steps, right? So 2 steps plus 2 is 4 steps. So it's also 4 steps, but ending up with 2. So all of these are, you can say minus 1, which is not viable. So that's it. That's all 4. Okay. So now we go 5. Okay. So now we go 5. So 5, I cannot double, so I can just do, let's say 4 plus 1, 3 plus 2. Now 4 plus 1, so we need to find 4, 1. We have double it, not double it, just paste. So that's going to be 5, 1. Right? 3, 2, so we need to find 3 and 2. Doesn't exist, so 5. That's it. 5 can only do 1. 6. 6 I can do 5 plus 1, 4 plus 2, 3 plus 3, or 3 times 2. So 5 plus 1, right? So it's 5, 1, so that's going to be a 6. So we're going to have 6, so 6, 1 is going to be 6. 4 plus 2, right? 4 plus 2, so we find 4, 2. So that's a 4, right? That's a 4. So we need to paste. So that's going to be 6, 2, going to be 5. It's going to be 5. 6, 2 is going to be 5. 3 plus 3. We don't have 3, 3, so that's no go. 3 times 2. So we just need something 3. And then we have a 3. And then the smallest is 3. Right? So 3. And then times 2 is copy and paste into plus 2 is going to be 5. And we're going to end up with 3. So 6 has 3, which is 5. 5 steps. Right? So that's 6. 7. Okay? 7, of course, we have 7, 1 is going to be that. It's 6 plus 1, right? And 5 plus 2. 5 doesn't have 2. 4 plus 3. 4 doesn't have 3. That's it. Now 7 is 7. I feel like this is the thing. This is the thing. 8. Of course we can keep going. Actually, the first column we can already fill it up, right? And then 8, we can just say it's 7 plus 1, and then we find that it exists. 6 plus 2, 6, 2, it exists. So we're going to result in 6 steps, right? And then 5 plus 3 doesn't exist. 4 plus 4 doesn't exist. We have 4 times 2, and so it's 6 and 4. So 4. So 6 right here. Okay, let's try this. So I modified the scheme. So the DP table is going to be minus 1 times n, n plus 1, right? And for this in range, n plus 1. Okay. We can prefill the entire first column, right? The entire first column. How do we fill? So we can just say for I in range, I don't know, 1 to n plus 1, dp I 1 gonna be I, right? So we pre-fill that, and once we fill that, we don't even need to fill that. Oh, we do need to fill that. Okay, we do need to fill that. So now what we're gonna do is check every value. Right, we can just start from 2, right? Start from 2. So we're gonna check every value, and 2 is actually, hold on, 2, because it can do 1 times 2. So we find 1, yeah, and then we can do 3 steps to end with 2. It's actually possible. 3 steps. It just requires 3 steps. right? So we copy 1, paste 1. No, hold on. That's already done. That's already 2. Yeah, that's already 2. It's so I will copy 1 again and paste 1 again. So I already have 1, and I copy it and I paste it. And that's just stupid. Yeah, let's just not do it. So we can do 1, 2, 3. Let's start from, I don't know. Let's start from 4. I can start from 3. Let's start from 3. Okay. So let's say for I in range 3 and plus 1. So 3 to n plus 1. Right? So for everything, I need to break it down. Alright? To break it down. How to break it down? Let's say for that's not j, okay? Because it depends. Actually, it is j. For j in range, I kind of that's fine. That's fine. So for j in range what? Well, it's going to be I minus 2. Alright? Because I minus 1 already done. And something plus 2. So I minus 2 all the way down to I don't know, divided by 2 plus 1. So if it's even number, okay, if it's odd number 3, no. So j is the bigger one, right? I want j to be the bigger value. So if j is the bigger value, let's just do I plus 1 divided by 2 plus 1. So in this case, if I is an even number, let's say 6 plus 1 is 7. 7 divided by 2 is 3. 3 plus 1, so we're just ending at 3, right? Which is fine. If it's 7, that's 4. We're ending at 4. Yeah, that's 4. Yeah. And then we'll do minus 1 here. Okay, so we have j. Now what? Now we just say if dp Wait, hold on. J is a small one. Come on, man. Come on, J is a smaller value. J is the smaller value. You dummy. Let's be this. J is a smaller value. So if dpij, not dpij, dpi minus j, alright? Is say j is the smaller value. Yeah, might as well just start from 1, right? Might as well. So dp 1 equals dp equals 1, and dp 1, no 2 1 equals 2. Might as well just start from 1, and then I start from 3. So this one's 2 1, right? So we say 2 plus 1, and then we just do a paste, right? We say if this one is larger or equal to 0. Actually, I can just do 0. And then we just say if this, right, has a value, then we can say dp ij, right, equals dpi minus j plus 1. Right? Okay. So if that exists, we do this. And then this will handle a lot of situations. So all of them will handle it. And once this one is done, if it doesn't exist, then this remains 0. Once it's done, now we can say if, right? We say if I mod 2 is equal to 0, which means that I can divide it by 2. Then we also need to check. And dp, say, I divided by 2. Oh, we need to find the smallest value on that. And then we say min, we say m equals the minimum dpi divided by 2, right? We say if m is not equal to 0, then what do we do? If m is not equal to 0, then we're going to say dpi You know what? I don't like it. I do not like it. I like to do this. So everything that shall be the minimum dp ij, and then this. Okay? And then if this, I'm going to say dpi, that's not j, because I copied I divided by 2 and I pasted it. So that's going to be I divided by 2, right? So this shall equal to minimum, of course, dpi, and I divided by 2, and minimum of this plus 2, copy and paste. Okay? So that's that. And then we're going to return the minimum of dpn. Lists index out of range. Out, of course, it's out of range. If n equal to 1, return 0. Okay, I passed everything. Let's try this one. This one definitely is a lot more promising. Okay, hold on. I still use the test cases here. I probably don't do all of them, just in case I might time out here. Yep, I think this one's right. Come on. Yes. Oh, yes, I passed with terrible result. 2,420 milliseconds. 5%. Well, I still pass. Okay. A little bit pat on my back. Whew. So you're saying this thing can be optimized? I mean, I did do a lot of min. I did. So these are O1s, and this is just O1000 every single time. Can we just I know, because we didn't use 0 position. All right, so we can do this, right? And we can say dpi0 equals minimum dpi0 and then dpij, right? You just do the j, so we just do that, right? So after we've done this one, so equal to minimum of this, and we don't have to do this, that is just going to be dpi0. And this one is, we don't have to do this because all we need is 0. What the heck? Oh, because after this, we have to redo this one more time. So that shall be I divided by 2. Right? Because I just did a new value, so I need to update it. 0, 1, 2, 3. Oh my god. What if we do this? We start from 2. There we go. We don't have to do this one anymore because we can do this dp1 0 equals this. Okay. Not sure if it's faster, but let's write some stuff. So we build a basically it's n plus 1 times n plus 1 matrix 2D array, not matrix, 2D array. And dp ij is the number of steps to take to reach value I with the final with j being at the copy board, right? Being at the copy board. So for any value, let's say k, we go through k minus 1 plus 1, k minus 2. We go through these pairs. K minus 1, 1, k minus 2, 2, all the way to k divided by 2 and k divided by 2. Right? And for each pair, we go to dp k minus v and v, right? If we go to k minus v and v, and we know that by a single paste action, we can go from k minus v, v to k. Thus, the steps needed to get to dp k v is dp k minus v, v plus 1. Also, if k is even, there is another way to reach k, which is from k divided by 2 and whatever, multiply from this and then do copy and paste. Thus, we need to find the min value of the row dp k divided by 2, and then add 2 more steps to it, and we get dp k divided by 2. So runtime is on squared. I think this one will be faster because I constantly updating the largest value. I mean, kind of on. That's actually the same. No, I think this is the same. I'm just using using the 0 for it. I think it'll be the same. Huh? Oh, shoot. You gotta be kidding me. dp10 is equal to 0. My bad. Ah yeah, this error could have been avoided. It's too long. That's why. Can't see. It's the same. It's actually even slower. So I'm just gonna record this. I'm gonna do it once. And now I have to do it every single time. You know what? I like this one. I'll revert to this one. Oh, with a slight difference. Yeah, the min, I think, maybe just slightly faster. Of course, this has to go to 2. Yeah, I think this is faster. So 2420. Well, technically, we have another min here. So I can call that another n. Oh, that's fine. That's on. This is n. This is another n. So yeah, it is true. But only 5%. I know this one's 5% as well. All right. So we need to check the solution. Prime factorization. Ooh. What the heck? There are better solutions. I try to study this one. It's only ON space. I times j is smaller or equal to n. The hell is this? Well, I can break our moves into groups of copy paste. Let C denote copy, P denote pasting. In a sequence of moves, the groups will be copy, paste, 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 copy, paste, 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 copy, paste. Okay. After parsing the first group, there are those A's. After parsing the second group, there are what? Have 3. And then copy. So we start from 3. Right? And then, so copy is 3. And then paste, paste, paste. So 3 times 4. Right? But plus 3. Plus 3 times 5. 3 times 5. Okay. So 3 times 5. That's 15, right? And I copy and paste. I do, and then times 2. Ooh, how did you get to this insight? Huh. Okay. If one of these is composite to 2 groups, such a split never uses more moves. We use P plus Q moves on split and PQ moves previously. This is equivalent. So P plus Q is always smaller or equal to PQ because, yeah, so it's true as long as P is larger than 2. It's prime factorization of n. Oh wow, what a solution. I want to find all the prime factors. How do we do prime factorization? I find the prime, so start with D, and then we get rid of all the primes, right? And every time we do this, and then D plus equal to 1. Yeah. We get rid of all the factor of the current one. And once we get rid of all of them, then we remove all the factors. So the only thing remaining, we have plus 1. Oh, God, this is good. Holy moly. I can be divided by j. So if sequence of length j can be pasted multiple times to get to length I, paste the sequence so the first length that I can do, so I is the current value, right? And this is ES, and then J from all the way to 1. So find the first J that I can copy. Then I say I will paste that J length. Okay, I will paste that J length that number of times. Was actually it's divided that minus 1 plus 1 times. And the first time we find that we can escape. The next smaller length sequence. Okay. Because why? What if we keep checking? Well, if we keep checking, we find a smaller, then this value will be larger. But this value will be smaller. How do you guarantee that? Value j can start from I divided by 2. Oh yeah, that's true. Yeah, why can we break? This is a good solution. Good explanation. Yeah, so it has to go back to the, so it's not really a DP solution, right? You have to go back to the sum of all primes. It's a sum of all primes. And then once it's the sum of all primes, then the prime factors, then you say, okay, it doesn't really matter which one we go first. Okay. So let's do, nice. I feel like this type of DP solution is, this is the official. I want to go with the official one. Official solution. It has a great proof that the minimum steps equals the sum of all prime factors. Because you can break it down to copy, paste, paste, copy, paste, paste, copy, paste, paste. And then you find out that after a such sequence, if you find the length, that's the number of A's first. And then for the next one, the number of A's will be the first sequence times the second sequence. So just the multiplication of these. And you'll find out if we break it open, right? If we break it open, it will always be, yeah, if one thing I can break it open, then the sum is always smaller than the, so but it becomes a sequence of all the prime factors. So we just need to find prime factors, right? And how do we find prime factors? So we have result is going to be 0, right? So P prime factor start with 2. And then we say while n is larger than 1, right? Because when divide to 1, that's the end. So while n is larger than 1. And then we say while n mod p is equal to 0, right? So which this can divide. Then we say res plus equal to, what do we want? We will want not a number. It's the sum of all prime factors. So we have plus equal to p prime factors, right? And then n divided equal to p. And then we try it again. So this one will get rid of all the factors is p. And then we can p plus equal to 1, all right? And in fact, I can get rid of 2, and then, yeah, I think I'll do it like this. Res is 0, right? Hold up. I say 2 plus equal to 2, and then divide by 2. So while n is larger than 1, and this, okay? So now we set to p to 3, and then I can do p plus equal to 2. So we save some, you save a tiny little bit. What the heck, man? Just save a tiny little bit. I just save the one operation on here. What's the point? So we just do this, right? And then we're going to return res. Holy guacamole. Yeah, this is a very good problem. Well, I'm happy I solved it, but with flying colors. Solve it with flying colors. Yeah. 37. Alright, so that'll be it. Wow, it's pretty hard. I'll see you guys tomorrow. Adios.